Good afternoon, folks. How are you today? In the last lecture, we started by looking at methods to solve a linear system, Ax is equal to b, where b is not zero. We looked at exact methods. I showed you how Gauss-Jordan elimination works. I did an example. You saw how matrix inversion works and how to get matrix inverse using Gauss-Jordan elimination. I hope you have done the examples yourself manually. You will need to do them on your quiz as well as on your test. Our next category, we are going to look at iterative methods. There are many iterative methods. We are going to particularly focus on Gauss-Seidel method. So let's see, we just covered exact methods, but when we implement them on a computer, we know that computer with floating point round off errors is an inexact machine. So if these exact methods were implemented with no computational errors, we would get a true solution. Of course, with finite digit machines, we have round off error and it can propagate, result in significant errors. So what we do is we do use something called pivoting, which is like row exchanges or column exchanges, and scaling, which is like normalizing, very similar to what you did to determine conditioning of a matrix. And we do this to minimize round off errors. However, if our linear system is ill-conditioned, we can do nothing. What the pivoting and scaling does is it just minimizes error. If it was an ill-conditioned system, we have to be especially careful. But if it is a well-conditioned system, we don't have to worry as much about pivoting and scaling as in the ill-conditioned system. So let's look at iterative methods. Just like one equation, one unknown, here we begin with a vector. So we begin with a vector guess x old. Then we compute delta x. This computation depends on the method we use. And then our new vector is old vector plus this delta x. We repeat these steps until delta x is close enough to 0, matches one of our convergence criteria. So in Gauss-Jacobi iterative method, what we do is we calculate the delta x for any element, that means for any single unknown, by taking the corresponding B element, taking the corresponding row of A times the old vector, and this difference, if we divide by the diagonal element, notice diagonal element therefore must not be 0. Ideally, we would like this diagonal element to be as large in magnitude as possible. So we will get delta x. So key idea here is that Gauss-Jacobi always uses old x values on the right hand side. In Gauss-Seidel, what will happen is once we calculate, say, delta x1, we will have a new value for x1. So we can use that new value here. So here on the right hand side, the x vector consists of most recent values for the elements. And then we take this difference, divide by the diagonal element. Again, ideally we want diagonal element as large as possible in magnitude. What are the benefits of iterative methods? Iterative methods at most require n square multiplications per iteration. You may remember direct methods required n cube over 3 multiplications. Usually we don't worry about this 1/3 part, so we just say n cube. Well, we converge in one iteration. It's a direct method, so it required total of n cube multiplications. So therefore, if we converge in less than n iterations, then of course our exact method becomes efficient compared to direct method. Of course, if n is small, like 3, we don't expect to converge in 3 iterations. So we don't use iterative methods for small systems. We use them for large systems. Imagine if n is a million. Now we just need to converge in less than 1 million iterations. So for large systems, iterative methods can be very, very efficient. So let's look at our Gauss-Seidel method. So in our Gauss-Seidel method, remember, we definitely want diagonal element to be not zero. Should be non-zero. So let's see our system. Let's suppose we have the system 2, 3, -2, 1, -1, 3, 8, -2, 1. x1, x2, x3, and right hand side the b vector is 287. So notice, even though none of the diagonal elements are zero, ideally we want this diagonal elements to be as large as possible. So of course this is equation 1, this is equation 2, this is equation 3. So what order we write our equation should be of no importance. We could write third equation as first equation and so on and so forth. So it'll be nice if we could have 8 come up here. So we'll take the third equation and write it as first equation. So we have taken third equation, written as that first equation. Now we want in the second place the largest magnitude. So if we look here, we know that first one is larger than this one. So we are going to write the second equation, first equation. So this was third equation. Then we are going to write our first equation as second. So we are going to write 2, 3, -2, 2. And then of course the only equation that remains is the second one. So we have 1, -1, 3. This is 8. So we got lucky. We got very large magnitude numbers on the diagonal. This may not happen all the time. We may not be able to do it. In this case, we were able to do it. So I have the equations here. Now you will see when we are going to implement it in Excel, we will use them in this matrix form. But however, when we are doing calculations by hand, it is often easier to skip the step of calculating delta x first and then x new. What we will do is we'll go ahead and calculate x new first, and then the difference between the two would be delta x. That is just manually, it makes it easier for us to calculate. So for that, we have to do some work. What we have to do manually. So what we'll do is we'll take our first equation. So this is our first equation, remember, and we will try to get the new x1 value from it. So we'll take 7 plus 2x2, and we have only old value, minus x3, and we have only old value, divided by 8. So this would be our new value of x, old, old. Let's look at our second equation. From second equation, we'll try to get value of x2. So our second equation says 2 minus 2x1 plus 2x3 over 3. So of course we are getting new value of x2. We have both an old and a new value of x1. Since we have a new value, Gauss-Seidel says use the most recent one. We only have old value for x3. Okay, from third equation we will write x3. So from third equation we'll get x3, 8 minus x1 plus x2 divided by 3. So now we have both new values of x1 and new values of x2. So this is going to be our equation. Now take out a calculator and you should calculate along with me. Okay, first iteration. Now how should we choose initial guesses? Often you can just pick anything random. Often what people do is they start with x, all x's to be zeros. What I rather do is I imagine if x's was 0, I would get 7/8 here. So I use that as a guess. 0.875. Here I'll use minus 2/3 as a guess. And here I will use 8/3. I'm sorry, 2/3 as a guess, positive. 8/3 as a guess here. Okay, so that's our initial guesses. So we go to our first iteration. So we put in x2 old here, 0.6667, 2.667 here, and let's see what we get. So take out your calculator, please. 7 plus 2 times. I'm keeping 4 decimal digits. So my next is 0.7083. So while I'm at it, I can find the difference. And I'm only interested in magnitude. All right. Now I have a x1 new, so I'm going to put that in there. So I will have 2 minus 2 times 0.7083 plus 2 times I have only old value for x3. So I'll get 1.9723. So now I have both a new value for x1, new value for x2. I'm going to put it in there. And I'll get 3.0880. So my largest change here was 1.306. So obviously we don't even have a single CDD. We do one more iteration. So we have now old values for x2 and x3. We put them in this equation, x1 new. So we will get 7 plus 2 minus 7 to 3 minus divide by 8. So we'll get 0.9821. So now the difference is like 0.27. Okay. So we have new value for x1, old value for x3. We substitute. And the difference is 0.098. Okay, now we have new values for both x1 and x2. So we put it in this third equation, 8 minus 1 plus 2.006. Now our largest delta x is 0.27. So we have 0 correct decimal digits. And on we can go. So I hope you're doing these calculations along with me. Here is our manual implementation. Notice I've got my first iteration, I've got my second iteration, and then eventually we get 4 correct decimal digits. Actually 5 correct decimal digits here. This is 0.5 times 10 to the minus 4. 4 correct decimal digits, sorry. 4 correct decimal digits. Okay, but you can see this is not the way it'll be easy to implement in Excel. So let's see our Excel implementation. Okay, so here is our setup. We are given matrix A, so we have to type it in or read it in, however large it is. We need matrix B, we need to be given that. And what we can do is we can right now have just manually copied diagonal, but I could write a formula here that would tell us what the diagonal element is. Since I have an iterative process, let's say we give this iterate, and you have used this process when you did parametric study. Let's give this a name. Let's call this iterate. So when iterate is false, we are at the beginning of our iterations. When iterate is true, we will start iterating. So again, notice whatever I'm going to do, I'm going to just write a formula only in the first row, 4 cells in fact. Then it doesn't matter how large my system is, I'm just going to copy down those formulas. Same way, so let's suppose you have written this x1, x2, you can take all these and copy them down. So if you have 1000 x's, you can label them like that. Anyway, the one name I need is x new. So I'm going to take this and call this x new. It would also make easier if we call this also some name. So let's call this absolute delta x. So we have created 3 names. Let's check them. Always use name manager. So we have created 3 names. Okay. So our first formula is going to be if iterate is equal to false, we need some initial value. So what we are going to do is we are going to take this matrix B, divide by diagonal element. Otherwise, we'll always pick up X new from this cell D9, right? So we have initial guess, otherwise we always copy X new. What is our delta X? Now our delta X is special. So we are going to take B minus, and we are going to do a matrix multiply. So we are going to do matrix multiply of first row by X new. And then divided by the diagonal element. So that was our formula. So right now we don't have a X new defined, so it is giving us this value error. Okay, what is our X new? If iterate is equal to false, then our only new value we have is old, so X new is X old. Otherwise, it'll be whatever X old is plus delta X. Okay. This is absolute of delta X. Of course, I have all these errors because my X new is not completely defined. So I'm going to take all these and copy them down. And I will get these values. Okay. Now my next thing is I want to calculate what is my maximum of this absolute dx. That's going to be what is called vector norm, and we are going to talk about it. Then we are going to decide whether we have converged or not. Let's say we want 5 correct decimal digits. So I'll write, is this absolute value less than 0.5 times 10 to the minus 5? We'll write 0.5, 10 to the minus 5. And of course, we have not converged. So now I'm going to change this to true. And it is supposed to give me an error. That is because I am not in automatic calculation mode, probably. Okay, so this is what should have happened. When I change this false to true, it should supposedly give me an error message, yes, because I have a circular reference. Remember, this is the thing we did in lab number 3. So what we are going to do is we are going to go File, Options, Formulas, and switch from automatic to manual mode. We don't want to recalculate. Enable iterative calculation. We want to do one at a time, and we are going to put this to some very low value, 1e minus 100. Okay. So if I press F9, it has done one iteration. Okay. Press F9 again, 2 iterations, 3, 4, 5, 6, 7, 8, 9, 10. In 10 iterations, I have converged. I have 5 decimal digits in my answers, and these are my answers. So if we round them up to 5 digits, let's see, home, let's state them all for 5 digits. Not scientific. And you can see these are our answers, 1, 2, 3, bold and box. So you can see how easy it was. I just typed 4 formulas, set this to false, put up my convergence criteria, and I just have to press F9. And of course, if I'm doing million times, I'm not going to press F9. Instead, I'm going to go into File, Options, Formulas. And here, instead of saying when I press F9, do one iteration only, I could say do 1,000, up to about 32,000 or so iterations at a time. Okay, see, we can check this. Let's suppose we set this to 5 iterations. Okay, all right, we do this resetting, false. So we are at the beginning of the iteration, F9 to recalculate the false mode, and then set it to true. And as soon as I press F9, it'll actually do 5 iterations. We have not converged. Press F9 again, it'll do 5 more, so 10. Okay, so I pressed F9 twice, 10 iterations, and we converged. So you can see how we can really quickly solve a linear system using iterative methods. So you are going to implement this Gauss-Seidel method in lab number 5. Okay, let's look at convergence properties of Gauss-Seidel method. If matrix A is strictly diagonally dominant, then Gauss-Seidel method is guaranteed to converge to the solution with any initial guess. Doesn't matter which one you start with. What does strictly diagonally dominant mean? Strictly diagonally dominant means, let's say we have a matrix A, its diagonal elements truly are very large in magnitude compared to the rest. So if we look at this A11, we are saying A11 magnitude is larger than all the rest magnitudes combined. A12, A13, A14, and so on and so forth. Same thing, second row, this is going to be larger than all other magnitudes combined. So let's look at our matrix that we just worked with. 8, -2, 1, 2, 3, -2, 1, -1, 3. So I'm writing it here, okay? So we check 8 greater than 2 and 1, which 3, yeah. So this was 8. Diagonal element 3 greater than 2 plus 2, 4, no. So this is not strictly diagonally dominant. So here matrix A is not diagonally dominant. Gauss-Seidel is not guaranteed to converge. It may have diverged. In our case, it did converge. Now, Gauss-Seidel is a preferred method over direct methods even when matrix A is large, N is very large in size. Think about hundreds or millions. Sparse means the matrix has a lot of zeros. Fortunately, it turns out that most of our engineering problems when we model that result in large matrices are what are called banded matrices, meaning a diagonal and possibly one diagonal on either side are non-zero, but rest of the entries are zero. So this is called a banded matrix. And these diagonals could be 3 diagonals or 5 diagonals, usually no more than 5 diagonals, most often 3. In fact, it also turns out that these diagonal elements are indeed large. So these matrices tend to be diagonally dominant. Generally, they may not be strictly diagonally dominant, because strictly means AII is strictly greater than all the sums, right? But if we say it could be equal, not necessarily strict, then it is just diagonally dominant. And that often is the case in engineering problems. And therefore, even though there's no strict guarantee, but usually Gauss-Seidel method converges. So great thing is Gauss-Seidel method requires only n square multiplication per iteration. So suppose you have n is equal to 1,000,000, you just need to converge in less than 1,000,000 iterations. Also notice the round off error affects only the last iteration in a way, because you can think, suppose you converged in 7th iteration. So you can say, hey, whatever results were at the end of the 6th, those were my initial guesses. So I converged in 1 iteration, because you can start with any initial guess. So your only accumulation of round off error is to go from this to next iteration. So that's the beauty of iterative methods. Okay, let's look at vector norms. So in fact, we have been using vector norms without defining them. So we have a vector, let's say x equals to 5, 7, -1, 2. So the first is our distance norm called L2 norm, also called Euclidean norm. So what this is we take square root and add all that square. So 5 square plus 7 square plus 1 square plus 2 square. And that becomes our vector size. So you can see this is like length of the vector. So you have seen it in other classes. So this is very useful when you want to find length. So we'll get 8.88. Okay. The other one is called the max norm. So what we do is we find whatever is the largest magnitude element. And then there are generalized norm like LP norm. So which is basically what we do is we sum up all the magnitudes, element magnitudes, raise them to power p and then add them. And then take the pth root. So this is called p norm. So you can see our L2 norm is when p is equal to 2. Let's try when p is equal to 1. So that'll be our L1 norm. So it'll be sum of x to the power 1, 1 over 1. So it's just adding all the magnitudes together. Right? So let's do this. So we add all of them. We'll get 5 plus 7 plus 1 plus 2. So we'll get 15. So this is usually very useful if you want to average out errors, for instance, because you want to only concern be magnitude of error, not sign of error. Positive and negative errors, they will cancel out. So often L1 norm is very useful in calculating average error.